So that's what we're going to say first of all. When we talk about simple harmonic motion, simple harmonic motion is going to be motion that repeats. But I want to, before we get to that, I want to talk about like certain properties of a spring that allow it to cause simple harmonic motion. So here's what we're going to do. So you can title your note simple harmonic motion. Or SHM for short. And we're going to start with something that you've actually seen before, but we haven't, we didn't discuss the last time, because we've talked about springs before. Anybody remember what we talked about with springs before? Yeah. We talked about elastic potential energy, right? And when we talked about elastic potential energy, we talked about how, like, you had to have a way to characterize how strong your spring was. Anybody remember how we characterized how strong the spring was? Yeah, great. The spring constant, which we use the letter K for, right? So the idea of a spring constant is how stiff a spring is. And what we're going to do is we talked about the energy in the energy unit. What I want to talk about today is not the energy. I want to talk about the force that's exerted by the spring. So now, as you pull a spring, right? You can imagine this. This is a spring that's would be like a tensile spring, right? It's a spring that I put tension in, I pull it more and more. You can also have a compression spring, right? You've seen these things. They're like in pinball machines, right? You know, in a pinball machine, there's a spring, and you have to pull the spring to compress it, right? So there are two types of springs, but they both have a spring constant. This spring that I'm holding, like I pull it, or you could have a spring like, if I imagine a spring like attached to the wall, if I pushed it, it would push back, right? The more you push that spring, the more the spring would push back, right? So in other words, what you would expect if you were to graph the force that a spring exerts, if you graph the force across how far you compress it, and actually I'm going to say absolute value of force, based upon how far I compress it, right? The more I compress it, the more force there would be. To be something like this, right? What all this means is that, remember, X means how much you compress the spring. All this means is as I compress the spring more and more, I get a larger and a larger force, right? Now, the slope of this graph is going to be what we call the spring constant. So we're going to refer to the slope of this graph as K, or the spring constant. Anybody remember the units of spring constant? Well, you can think about it, if you think about it as the slope of this graph, right? Slope is rise over run. What am I going to be measuring my rise in if it's force? My rise in newtons, my run is going to be in meters, and so the units of spring constant are going to be newtons per meter. The other thing we can say looking at this equation is we can write looking at this graph is we can write an equation, right? This is just a line. It's a line that has a y-intercept of 0 and a slope of k. So what we're going to say is that the force exerted by a spring is equal to kx. Right? Because if you think about y equals mx plus b, y is the force, k is a slope, x is x, and then the b is 0. Right? So this is the equation that talks about the force on a spring. But I got to add something to the spring, because the thing is that spring is always going to fight against what you're trying to do to it, right? So the reason why I wanted to graph the absolute value of force is because technically the equation is force equals negative kx. And that makes sense if you think about a spring, because again, in this case, if I try to pull this spring, if I try to pull it this way, the force is always opposite of which way I'm pulling it, right? If I try to pull it this way, the force is up, right? You think about a compression spring, right? You have a compression spring attached to the wall, and I try to push the compression spring this way, it's going to pull, it's going to push back against it, right? So that's why there's a negative, because the force always fights against what you're doing, right? This is what is called, so the name for this relationship, F equals negative kx, this is called Hooke's law, named after Mr. Hooke. I don't remember what his first name was. All right, now, how do we use the fact, the next thing is we can use Hooke's law to explain why this thing undergoes simple harmonic motion. And again, when I say simple harmonic motion, all I'm referring to, I'm going to give you a more precise definition in a second. What I'm referring to when I say simple harmonic motion, that's how when I hang this mass from this spring and I start it, it just goes back and forth forever, right? This turns out to be a direct consequence of Hooke's law. So what I'm going to do is I'm going to imagine, actually, instead of a spring that's hanging up and down, I'm going to imagine an object that's on a surface like this, but we're going to say it's a frictionless surface. So I'm going to put this object here, and I'm going to attach it to a spring that's hooked to the wall. And what I'm going to do is I'm going to say that at this point, right, I'm going to say that this is the point where it like naturally wants to be. This is a point we're going to call equilibrium. So I'm just going to kind of drop a dotted line down here, because what I'm going to do is I'm going to plot the location of this object over time. So I'm just going to drop this dotted line here. And I'm going to call this the equilibrium point. And what I want to do is I want to imagine what's going to happen if I try to push this thing this way, right? So if I try to push this thing this way, so let me redraw this. This is going to be the same spring, but at a different point in time. We're going to imagine that I cause it to compress. So 6, 7, 8, so I'm going to take this and I'm going to cause this thing to compress. So now it's here, right? If the object is here now, I'm not doing a very good job of keeping it the same size, but you get the idea. All right. If this is here now, so I've pushed it this way, so now it kind of has a negative x. Which way is the force going to point now? Now the force is going to point out. So I'll draw it up here, I guess. Right? Because of Hooke's law, what's happening is, so if this is like x equals 0, if I give it so that it has a negative x, right, the force is going to push it back out, right? And then what's going to happen is it's going to push it back out, and it's going to push it back to equilibrium. And you might think that it would stop at equilibrium, right? Because equilibrium is where that spring naturally wants to be. But why does that object not stop when it gets to equilibrium? It's frictionless, so why is that important? What were you going to say? Right idea, wrong term. It's not that it's still got force. It's that it's still got momentum or inertia or whatever, or it's still got speed, right? It's still moving, it's in motion, and it wants to stay in motion, right? And so what's going to happen is instead of stopping at equilibrium, it's going to go all the way out here, and it's going to now stretch out the spring. So and then again, now I'm going to have a positive x. So if I have a positive x, the force is going to be negative, and it's going to try to push back. This is going to be something that we're going to call, this force is going to be something that we're going to refer to as a restoring force. Because it always tries to restore it back to equilibrium. But one of the things I like to say is that simple harmonic motion is one of the great tragic stories of physics. Because it's the story of the persistent failure of the restoring force to achieve its purpose, right? The restoring force has one job. The restoring force is trying to restore it back to equilibrium. But once you get simple harmonic motion started, the restoring force continually fails to achieve that objective, right? So you compress a spring, the restoring force tries to pull it back to equilibrium, but then it's still got inertia, so it carries it past, right? And now the restoring force tries again to pull it back to equilibrium, but there's still inertia, so the inertia carries it past. And then the restoring force pulls it back to equilibrium, but the inertia carries it past. And the restoring force pulls it back to equilibrium, but the inertia carries it past. And the restoring force pulls it back to equilibrium, but the inertia carries it past. And the restoring force pulls it back to equilibrium, but the inertia carries it past. And the restoring force pulls it back to equilibrium, but the inertia carries it past. But then the restoring force pulls it back to equilibrium, but then the inertia carries it past. And this time the restoring force pulls it back to equilibrium, but the inertia carries it past. And then the restoring force pulls it back to equilibrium, but the inertia carries it past. And the restoring force pulls it back to equilibrium, but the inertia carries it past. And then the restoring force pulls it back to equilibrium, and the inertia carries it past. Isn't that a sad story? It's a deep tragedy, right? The restoring force always fails, right? And again, in the absence of any sort of friction, that'll go on forever, right? You can think about this from an energy perspective. Right? From an energy perspective, initially, so if I don't compress it or anything, right, it's going to have no energy. But if I put work on it, right, if I put work on it to compress this thing in, now what kind of energy does it have? Potential. What kind of potential? Elastic. It's got elastic potential energy, right? That converts to kinetic, and it's back to full kinetic at equilibrium. But then, as it stretches, it becomes potential again. And then it's kinetic potential, kinetic potential, kinetic potential. But if there's nothing to slow that thing down, right? It's kind of like, I don't know if you remember when we did energy. Do you remember the skater on the FET lab? And the skater, if you actually really had a frictionless ramp, the skater went back and forth forever, because you had nothing to take it out any energy. It would change back and forth from kinetic potential, but there's nothing that ever got rid of it. So this simple harmonic motion. So now I'm going to give you a definition for simple harmonic motion. This is the definition. So simple harmonic motion is motion that repeats due to a restoring force that obeys Hooke's law. Oh, sorry. I don't even have it where you can see it. Sorry. Simple harmonic motion is motion that repeats due to a restoring force that obeys Hooke's law.
when I say repeats, there's another word that I'll use that maybe you've heard before. Well, let me just, I'm going to define a few terms for you here. Oscillation, amplitude, period, frequency. These are 4 words I'm not gonna actually write down definitions for, but we're gonna talk about them. Anyone heard of the word oscillation before? Yeah. You know what I mean? Yeah, an oscillation is a back and forth, right? So you're maybe thinking about it in terms of a sine wave, right? And we're actually gonna, so if we wanted to graph this motion, it actually makes a sine wave, and we'll get to that. But an oscillation is just back and forth. That's what it means. So one oscillation, if I get my spring out again. So an oscillation is one complete back and forth, right? So here, down, up, that's an oscillation, right? So that's 1, 2, 3, 4, right? A complete oscillation is one back and forth motion. I don't know, guys, if you remember, you know what an oscillating fan is? Yeah. So an oscillating fan is a fan that does this. An oscillation just means back and forth. All right. Amplitude. When I refer to this, we're specifically going to talk about the amplitude as how far this thing, the maximum displacement of this thing from equilibrium, right? So if I were going to draw that on this picture, like I could call this the amplitude. And again, that should match if you're in trig and you've been talking about sine waves, right? It's the same thing. When you define the amplitude of a sine wave, it's how tall the sine wave gets above 0, right? It's the same thing here. If you got this, so there's always going to be an equilibrium point. But right now, this thing naturally wants to hang there. You can think about this as the 0 point. If I start this thing oscillating, right, how far I get above the equilibrium point is the amplitude. And it should also be, if I have my hand in the right place, it should be symmetrical, right? So you should get just as far above equilibrium as you do below. That's called the amplitude. All right. The other two, and these are the most important terms on here, period and frequency. Now, we've actually referred to, we talked about the period of motion when we talked about circular motion. You might remember what the period meant in terms of circular motion. Yeah, right, yeah, it's the whole circle, right? The time it takes to go the whole circle. You might remember the symbol we used for it? It's capital T. The reason why is because period is just a time, but it's a special time. So in a circle, the period was the time it took to complete the circle. In simple harmonic motion, the period is going to be the time it takes to complete an oscillation. Frequency, and I don't think we've talked about this before, but you might know what frequency is. Yeah. Yeah.
Like how fast?
Basically, yeah. So period is, I might write these two down. Period is going to be the time of one oscillation. Frequency is going to be the oscillations in a period of time. So they're kind of like opposites of each other, right? And we're going to use the symbol for frequency, lowercase f. Now be careful, it has to be lowercase f because capital F is force up at the top, right? So capital F is going to be force, lowercase f is going to be frequency. If you take chemistry, sometimes they use nu, a little V looking thing. So if you remember, if you did chemistry, what was it? You talked about Planck's constant times the energy with Planck's constant times nu, V equals H, or E equals HF, or E equals H nu. That's the same thing. We're going to measure period because it's just a time. We're going to measure period in seconds. we're going to measure frequency in units called hertz, Hz. Hertz just means oscillations per second. If you have one of those really old radios that still has a dial on it, and you look at like the FM and AM bands on the radio, you'll notice on the side of the band, FM is measured in megahertz, AM is measured in kilohertz. Again, those your radio receives radio waves, right? And those waves have a frequency. So the frequency is, so like FM is in megahertz. So if you're listening to ZPL, right, 99.5, that means 99.5 megahertz. So it's receiving a signal that oscillates 99.5 million times per second. That's what that means. Now, what I'm going to do with these is I'm going to give you the only 4 equations all year I'm going to ask you to memorize. The only 4 equations I will not give you. Period is going to be time divided by number of oscillations, right? So again, that makes sense because it's the total time something travels divided by how many oscillations it made. Frequency is the opposite. Oscillations divided by time. And then I'm going to give you, that's period and that's frequency. They are, you'll notice they are reciprocals of each other. So I can also say that period is 1 over F and F is 1 over T. These are the only 4 equations all year I'm going to ask you to memorize. But the reason I don't give them to you on the test is because if you have the equation, you have the definition. So I think it's important that you know the difference between them. All right. Yes, sir.
Are metronomes like harmonic motion?
They let me think about that. Like the old style metronome, yes, yeah, yeah. That would still be sitting harmonic motion. They would all be harmonic motion. I just have to think. Sometimes you got complex harmonic motion, but yeah, the old style metronomes are mostly just they've got straight M. Now you would probably not be measuring those in hertz. You probably measure those in dB per minute. But, yeah. All right, I got a couple of example problems here. Don't know if it was worth the paper to print this, but I thought it'd be easier to write it down. By the way, as far as the memorized equations go, I'll just tell you that you are going to naturally memorize them as you go on. I don't think that you need to go home tonight and hit yourself on those. Maybe you'll need to do that if in 3 weeks your slot and you'll get up every time. But I think you're going to find that we're going to do this enough that you're going to figure it out. All right. What I'd like you to do is I'd like you to see what you can do with number 1 on here. Everyone get one. Not sure what this question 1 is talking about, right? Here it seems something like this is the grocery store. That's what I've been asking, right? So something like this is the grocery store that's got a basket hanging off of it, and as you hang something off of it, right, it reads the a weight, right? Well, the way it does it is because there's a spring in here, right? There's a spring, and the spring is attached to the dial, right? So what you're really doing is you're really, this is really going to be the place of the spring, and then you calibrate it to say what the weight should be, right? So my question is, so here are my oranges, right? I hang my oranges on the spring. My question is, what distance did that spring stretch? So see what you can do with that. Don't know if we've actually done things with our new partners yet. So just take a moment to introduce yourself to your new partners. Who's ever sitting next to you in these two rows, you guys are partners. Who's ever sitting next to you in these two rows, Val, your partner's not there, so you're going to have to do it for 3 then. You guys are partners. You guys are partners, and I think we got a group of 3 at the back. So, yeah. And yeah, Logan, your partner's not there, so we'll do a group of 3. All right, so see what you can do with this with your partner.
It's like 100.
All right. I got some knowns and unknowns up there. I'm okay with that. But I didn't put what, the force centimeters is 0.04 meters, right? I didn't put what that is. Anyone want to tell me what symbol that is? Probably X, right? That's how far the spring got stretched. All right. I got an idea how to do this. Okay. Good. So we know that what is the force that's stretching this? The force that's stretching it is gravity, right? And if you and what's actually going to happen is, if you actually do this, right, what's happening is the spring is going to push up against it. The idea is you shouldn't end up with, well, let's see here. So force is gravity, mg equals negative kx, right? Yeah. Yeah, so you can do this. What I want to make clear is there are different ways to solve this, but K should end up positive, right? The way that I think of K turning out positive in this case is we know that X and the force are going to be in opposite directions. So in this case, right, my X is probably going to be negative. But the idea is if you ever come out with a negative K, you just need to look at your negatives and make sure they're working out correctly. So did you get an answer, Leo? 102.5? 22.5. Yeah, newtons per meter. All right with that? Before you can do number 2, I'm going to have to give you one more equation. Everyone okay with 1? All right. So number 2, what I'm going to say is I'm going to just give you an equation out of nowhere for now. because I think that you need to get used to the equation before we derive it. We're going to derive it next time, but I'm going to give you one more equation, and that's the equation that tells you the period of a spring. So the period of a spring, and I'm going to use this because we're eventually going to have more than just springs. So I'm going to call this TS. So the period of a spring is going to be equal to 2 pi square root of, I always forget if it's m over k or k over m. So give me 1 second. M over k. So that's the new equation that you need. Again, it's weird that there's 2 pi in it. Just trust me for now, that's the equation. I'll tell you next time why that's the equation. But for now, see if you can use that to try T. Let me just give you a hint that might be helpful to you. It's a hint that you don't need, but as we go on, it might be helpful to have. If that's the period equation, since we know that period and frequency are inverses of, or are reciprocals, right? If that's the period equation, we can also say this, right? We could say that the spring frequency is the reciprocal of that. So like when you get to the test, I'm only going to give you this equation, but this equation implies this equation, right? Because frequency is 1 over period, right? So that might help you to use that equation. How far are we getting so far? All right. Any thoughts? Well, let's maybe start with what we know, right? So we know at first, when I put a mass of 0.6 kilograms on it, I get a frequency of 3 hertz. Then when I put a mass of 0.38 kilograms on it, I get a frequency of, I don't know, right? Good. Yeah. thing that's going to be the same for both of these is it's the same spring, so it's got the same spring constant, right? So what I can do is I can, if I can get K here, right, I can use that K over here. So, so let's see here. So if I plug in, I got 3 equals 1 over 2 pi square root of K over 0.6. Right. And there's a little bit of math you got to do, but 6 pi equals square root of K over 0.6. So 36 pi squared equals K over 0.6. Somebody double check me on that. Right, okay. So now I can go frequency 1 over 2 pi square root of K, that's the same, divided by my new N, which is 0.38 kilograms. Okay with that? If you're interested in following through the units, let me just show you real quick how the units work out, right? So a Newton per meter, if you recall, a Newton is a kilogram meter per second squared because it's F equals MA. So if I have a Newton times a meter and I divide it by a kilogram, sorry, Newton, sorry, sorry, a Newton is just a kilogram meter per second squared, I'm sorry. So it's a Newton divided by a meter divided by a kilogram, right? What happens is your kilograms cancel out and your masses cancel out. So I'm left with the square root of 1 over second squared, which is 1 over seconds. The name for 1 over, remember Hertz is oscillations per second. So a Hertz is a 1 over second. So if 1 over a second comes out of the equation, you get Hertz. Any questions on that? Okay. Syllabus-wise, you are now able to do the first section. I don't have that due until Tuesday, so we'll have some time, more time to work on it. I'm actually not sure that you can do all of those problems yet, but you can at least do the first several.